One of the most important effects that has a great influence on the transport properties as well as some other magnetic properties, spin-dependent transport and magnetic properties of solids is spin-orbit coupling. In a nutshell, it's the interaction of the magnetic moment from the electron spin with the magnetic field that is created by the orbital motion of the electron. So let's note this, the magnetic moment of the electron spin which I denote by m sub s interaction with the magnetic field due to the orbital motion of the electron which I denote by h suborbital is called the spin orbit coupling. So I'm going to work with the same semi-classical model, and we will gain a great insight into how spin orbit coupling works using this model. So if you remember, in our classical model, basically we have considered the electron to be a disk which has its charge uniformly distributed in the perimeter of the circle, and it rotates around the z-axis, and it creates a magnetic moment due to the angular momentum, the spin angular momentum of the electron, and that's basically creating a current. Current multiplied by area is the magnetic moment due to spin. So now we know that from this model, the magnetic moment due to spin m sub s is, let me write it, let me have the sign denotes the direction here, minus g Bohr magneton m sub s. So this I have used mu sub s here in order to not have a confusion between the magnetic moment and the spin quantum number. So I have used mu instead of m in order to have the spin quantum number included. And since the lambda factor is 2 and spin quantum number is one half here, so we're going to have minus mu bar. So spin contributes, a spin 1/2 particle contributes a magnetic moment of a Bohr magneton to the total magnetic moment, which is minus e h bar divided by twice the mass of the electron. And the current is due to the spinning of this disk. It's basically minus the electron charge divided by the period t. So it's going to be minus the electron charge v divided by 2 pi r, where r is the radius of this disk. So let me call this rs. It's for the spin, 2 pi rs. And Basically, actually, I want to look at the current created by the orbit, not by the spin. So let's have this Rs and Rho for the orbit. So the current due to the orbital motion of the electron is minus ev over 2 pi r0, our orbital radius. So the v, the tangential speed, is 2 pi, the orbit radius r0, divided by t. So this is the orbital motion. Okay. Now, what is the magnetic field created at the center? So let's think about the magnetic field created at the center. Well, if you have a current loop which has a radius r0, we know the magnetic field created by this current loop is I divided by 2 r0 using SI units. And since the current is minus EV divided by 2 pi r0, and we have a factor 1 over 2 r0 here for the orbit radius. So this would be equal to minus EV divided by 4 pi orbit radius squared. And at the same time, we have the angular momentum is quantized, and the orbital radius r0 is m sub l h bar. So for the tangential speed, we can use the quantum mechanical result, m sub l h bar divided by mass of the electron times the orbit radius. So if you substitute this into this v, we can get the magnetic field at the center to be minus E over 4 pi orbit radius squared, and for V I'm substituting m sub L h bar divided by mass of the electron times the orbit radius r0. So this gives us minus E h bar m sub L divided by 4 pi mass of the electron orbit radius cube. So I have two ingredients ready for me. One is the magnetic moment of the spin. Two is the magnetic field at the center. So basically I'm looking at the interaction between the magnetic field at the center and the magnetic moment of the spin. So the energy of a dipole in a magnetic field, I recall, in a magnetic field H, once again using SI units, this energy is minus mu 0, the spin magnetic moment dot product with the orbital field. The field due to the orbit is negative here because of the minus sign of the electron, and here I have a negative moment as well. So therefore two negatives make positive. I already have a minus sign, so the minus sign is retained. So I will find minus mu 0 Bohr magneton divided by, so let me work on this H a little bit here in order to make this look nicer. This is minus 1 over 2 pi r0 cube multiplied by EH bar over twice mass of the electron times m sub l. So this can be written as minus a Bohr magneton, the magnetic quantum number m sub l, divided by 2 pi r0 cube. So if I substitute that for the magnetic field at the center, so here I will have minus mu 0. I have one Bohr magneton from the spin magnetic moment. So I will have another Bohr magneton from the orbital field. So Bohr magneton squared. Then I have m sub l cosine of the angle between them I call cosine theta, divided by 2 pi r0 cube. So I have substituted minus a Bohr magneton m sub l divided by 2 pi r0 cube for h orbital, and for spin magnetic moment I have substituted minus a Bohr magneton, so that gives me mu 0 times Bohr magneton squared m sub l cosine theta over 2 pi r0 cube. So this is the energy of the system. Now if the atomic number is Z, then we have the Coulomb attraction, then the Coulomb interaction would give us the following result. The force of attraction between the electron and the proton, Ze times E divided by r orbit squared, this must be equal to mass of the electron V squared divided by r orbit. So we can see that because of this, V square V square r orbit is proportional to Z, the atomic number, because I have cancellation of one of the r's here, and V square r is kZe square. K is 1 over 4 pi epsilon 0, it's a constant. Electron charge is a constant, and it's proportional to Z. Now I also have V is given by m sub l h bar divided by mass of the electron times the orbit radius from quantization of orbital angular momentum. So I can substitute this for V. Therefore, this gives me mass of the electron m sub l square h bar square mass of the electron square r orbit square times r orbit is proportional to Z. So you can see that we get rid of one of the orbit radii, and we get rid of one of the masses here. Now I'm left with the magnetic quantum number h bar, mass of the electron. All these are constants, and 1 over r orbital is proportional to Z. So my main conclusion here is that the orbit radius, r orbit, is proportional to 1 over Z. Now this is an important result I have to keep in mind. Then, because I have the energy of the spin orbit coupling proportional to, if you go back here, 1 over r0 cube, so this factor, basically I see that this energy proportional to 1 over orbit radius cube is actually proportional to Z cube. So the energy of the spin orbit coupling interaction is proportional to Z cube. Then so I can retain this result for future reference. And also the force, the spin fields, the electron spin fields, due to this interaction, is force proportional to gradient of energy, which is proportional to the derivative with respect to r, so it would give us 1 over r0 to the fourth power, which is proportional to z to the fourth power. So the energy of the spin-orbit coupling is proportional to z cube, and the force the spin feels is proportional to z to the fourth power. So that's an important result. So we can note that the magnitude of the spin-orbit coupling is determined by the charge on the nucleus. Which is determined by the atomic number Z. And the force due to spin-orbit coupling is proportional to Z to the fourth power. Therefore, spin-orbit coupling in hydrogen atom is negligible. So it would be very small because you have Z is equal to 1. On the other hand, if you have a heavy metal like platinum or palladium, etc., where the Z is high, the spin-orbit coupling would become quite large. Okay, so let's review what we said about spin-orbit coupling. It's the coupling of the magnetic moment due to spin with the magnetic field created by the orbital motion of the electron. The spin magnetic moment is a Bohr magneton. The orbital motion of the electron creates a magnetic field, which I can calculate at the center quite easily, I divided by 2r using SI units, or B is mu0 I over 2r if you wish. And by substituting the quantization of angular momentum, mvr is equal to m sub l h bar, into the current, which is minus ev over 2 pi r for v, I can get the magnetic field to be minus a Bohr magneton m sub l divided by 2 pi r0 cube. The energy of a dipole in a magnetic field H minus mu0 m dot H. So the magnetic moment due to the electron spin is negative. The orbital magnetic field is negative. So I have a minus sign here. The energy is minus mu0 mu b square m sub l cosine theta divided by 2 pi r0 cube. So it has a dependence on the orbit radius 1 over r0 cube. And using Coulomb interaction, I have shown you that the orbit radius is proportional to 1 over z, because you have v is m sub l h bar over m r0. So by using the quantization of orbital angular momentum, we see that the relationship between r0 and z is r0 is proportional to 1 over z. And since the energy is proportional to 1 over r0 cube, it's proportional to z cube, and the force, which is the gradient of energy, it's minus the gradient of energy, but it's proportional to the gradient of energy in magnitude. So it would be a derivative with respect to r, which gives you 1 over r to the 4 or z to the 4 dependence. So the magnitude of the spin-orbit coupling is determined by the charge in the nucleus. The force of spin-orbit coupling on the spin is z to the 4 has z to the 4 dependence. Therefore, this effect is negligible in low z atoms like hydrogen.